Hi, in this course on basic construction materials, today we will be talking about nature of materials. This is the third lecture in this module, in which we will be looking at plane and surface defects, plane or surface defects, and volume defects. In the previous lectures we covered electron configuration, atomic bonding, and also talked about lattice structure, lattice defects, and two types of defects. There are point and line defects, and today we will be talking about plane or surface and volume defects, and then also phase diagram. So, this is what we are going to cover today. These are the books which have been used in general for making this course material. These two books have been heavily used by Mamlok and Sanowski and Zeniewski and Callister. Okay, and also a lot of information from the internet have been used to really demonstration purposes. Now, plane or surface defects in polycrystalline solids. So, what is this? It is actually the interfacial zone between different crystals. We already talked about what is a lattice structure, what is a crystal structure, all that. Now, when two different crystals, they come together or they form a boundary which we call grain boundary, this one, and it represents an area of defect concentrations within the solid. Okay, and this occurs because the orientation of atoms is different in each crystal. Now, here you can look at this first picture here, first diagram on the left side. You have these green circles, okay, and also you have these. Okay, so let me just redo this, green and the white circles you have, and the border between the two, they kind of form the grain boundary. So, I can call here that I have a green grain and then a white grain, and then this region which is marked now is the grain boundary. Okay. So, this is depicted on the second drawing, where you can see the crystals aligned in a particular fashion like this. Okay, you can follow this black lines, that is the alignment for the crystals or in each grain. So, each of these region we can call it a grain. Okay, so, if I count how many grains are there in the second drawing, I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 17. So, you can see actually some of them of course partially visible, but there are 17 grains. So, it is very clear to you what a grain is. Okay. And similarly, its a real picture is shown on the as the third photo, the photograph on the right side. And here you can see there is a scale. In whenever we look at a microscopic image or a micrograph, we usually put a scale there. Okay. That is to really understand what is the the perspective or what is the range of the size of the grains which you see here. So, this is, if you look at this photograph from left to right end of the photograph, it is about 0.2 millimeter. So, you can see how small that is. So, each of these grain is even smaller than fraction of a millimeter. So, they are just very small, small in size, and you can see grain boundaries here. This is a grain boundary. Okay. So, like that there are, so all these grains and grain boundaries, the size, shape of each of them, how the alignment etc. inside the alignment of atoms inside the grain, all those matters a lot when we talk about the material behavior. Okay. Now, how these grains are formed when we make the metals? Okay, these are typically the nature of the metals. So, how do we make metal? We take raw material, we melt it and then cool it, and then the cooling is done in a different way, like the rate of cooling could be different. So, all sorts of things we do, but in general, if we ask how a metal is made, we can say that a molten material is taken and it is cooled down to solidify, and then we call it metal. This was covered previous lecture also. Now, the molten metal cools, the atoms lose their energy. As it cools, they lose their energy and form together into lattice structures. Okay, so they come together into lattice structures. Now, when this happens, what happens is this coming closer to each other and forming the crystals, that happens at different points in the 3D space of the molten material. It is not that it happens starting from the surface to go into the depth, or inside the material itself at different points, depending on that particular temperature at particular point within the 3D material or the volume, the crystal starts forming, and that point where they start forming, we call them nuclei, okay, or nucleation points. Now, they start forming, and then it forms into crystals in 3 dimension, and so you have this 3-dimensional structure which is formed and which we call as grains. Okay, you can even imagine a rice bowl. You have several rice grains in that, and then each rice grain will be hitting each other. That we can call, that hitting place we can call as grain boundary. I mean, it's not really comparable, but this, because of the word grain, I thought it is good thing for you to visualize. And then inside each rice grain there are several cells, or atomic structure is different, so all that. Okay. Anyway, so here I am going to show you this animation over here on how grains are formed and grain boundaries are formed. Okay. Now, you can see that there is more and more crystals are getting attached to the blue crystals, which, so now these black lines indicate the grain boundary. I am going to play this once more so that you can see it again. So, now you can see there are different nucleation points, and then crystals have grown a little bit, but not fully developed. So, this is one only here, one, and here you have 4, here you have 2 crystals together, and here there are cases with more than that together. Okay. Now, I will play this once more. You will see that each of this crystal grows in all directions and fill the space. And when they start filling, and that means if I am initiating one here, they start growing and start to hit each other, but the direction of growth in each cell is not parallel. Okay, or each crystal location is not parallel. So, when they grow and hit each other, there is a misalignment generated. So, I will just play once more, you can just watch. Okay, so it's crystals are growing, and then suddenly they start hitting each other, and then the entire space is filled. Okay. Now, the black line, along the black line, if you see, you can see that they are not in the same alignment. So, for example, here these are aligned in this way, whereas these are aligned in this way. Okay. So, definitely there is a change in the alignment or difference in the alignment, and that is what causes the grain boundaries to form. Now, let us think what is the effect of these grain boundaries, etc., in the cracking or fracturing of the materials or deformation of the materials. So, for that we will look at what happens when a material is pulled. Let us say talk about the example of tensile behavior. You can see here on screen, you have this arrows indicate the tensile direction or tensile force is acting, and there is a necking which is happening. So, this is that region which is necking. Okay, you can see the neck like shape, and what you see on the first picture is necking starts to happen. That means there is a significant deformation, already the plastic flow is generated, and then formation of micro voids is the first thing which happens. So, dimples and micro cavities are also there, you can see that here. Now, that small deformation happening there, and then what happens is eventually as the force, more and more force is applied, they tend to, all these micro voids tend to coalesce and become one macro void. Okay, or it forms like the large crack. Visually you will be able to see the crack happening. And then eventually as you apply more force, then there is more flow of material, and then that is shear deformation is happening. And now here you should also look at the direction in which this happened. There is an angle associated with that. This is what typically you will see in ductile material. So this slide is mainly on ductile behavior, not on the brittle material failure. Okay. Now here also on the last one, when actually the fracture happens, you can see that this is in this shape. So look at the photograph at the bottom here, which is like a cup and cone. So what you see is actually a cup of the, you can see this is the shape in which it is failed. So typical we call cup cone mode. You can search in the internet on how they are looking, cup cone failure. So when you pull the top portion here, the top portion here, it's like this, and the bottom portion is like this. So bottom portion is, it's like this. So here I can say the top portion, which is the same as the photograph here. Okay, it's just upside down, but that photograph is of the top portion. Here I can call that as the cone, and the bottom portion is the cup. Okay, so you know what is cup cone behavior right now. So, but still go read, in textbooks where you will get much more clear explanations on that. Now coming back, when this what is this fracture or how does it happen? If you look in a microscopic level, you can see similar to the crystal structure. So here you can see there is a crack. I have drawn this crack here on the same grain structure which we saw previous slide, previous to previous. So here this is the crack. Okay. Now crack. Okay. Now how it will look? If you look at this left side drawing, you can see all these blue circles are the atoms, and then the crack is actually breaking all these bonds. I mean, that when the bonds are broken, that is where the crack happens. So you are not talking like these atoms getting broken or anything, but the bond between the atoms, they just get broken. That is essentially what is happening. So even if you look at here in the right side, you can say that let's say if a crack is happening, it will be something like this, it will grow. Okay. So you can imagine that. Just wanted to show you how it is really happening, so that your mind starts thinking in that direction. Now when we talk these cracks or breaking of these atomic bonds, etc., there are two types of cracks in general. We can call it transgranular crack or intergranular crack. So the two terms very important to remember, trans or intergranular cracks. Now the transgranular crack means the grain boundary has high toughness. Why the transgranular crack happens? It means the crack is happening through the granules. Okay, or here we can call each grain as the crack is happening through the grain. You can see this thick black line in this drawing here on the right side top, the thick black line. So the arrows indicate the tensile force which are acting. Okay, so they indicate the tensile force which are acting. So I'm going to call it T here. So it's being pulled in the vertical direction, and then there is a crack which is happening. That's the thick black line on the drawing. Now that crack is going through the grains. You can see here, for example, it is this particular grain is actually broken. Okay, so the black line, thick black line is going, or the crack is going through the grains. Here also you can see it is going through the grains. It's through the grains. It's also happening through the grain. So all these are happening, or crack is going through the grain, then we call it transgranular crack. And why it is happening like that? I can say that the grain boundaries are actually stronger in that case as compared to grain themselves. Okay. So anyway, more energy is required to crack in general in this case, and then cracks propagate through the grains. Then fracture surface has faceted texture, because of different orientation of cleavage planes. I will show a picture on the next slide, then it will be very clear to you what I am talking here. Before we show that, or let me just show you that picture. So, this is on the left side here, this one. Okay, you can see that this is one grain, and then this is completely fractured here. Okay, so all these are happening through the grain, or the grain itself is cracked. Okay, now going back to the previous slide. So, now the second type of crack is intergranular crack, where grain boundary has in general low toughness. In the first case, grain boundary had high toughness and grains were actually weaker. In the intergranular case, you have grain boundary which is having low toughness, or fails earlier, or cracks or breaks earlier, fractures earlier. Now, typically less energy is required to crack in this, but again I am making a general statement here, but specific material to material, these less and more and all that will keep changing. But in general, this is the scenario. Now, cracks propagate through where? They propagate through the grain boundaries or along the grain boundaries. You can see here in the bottom right image, you can see that they are actually going along the grain boundaries. They are not really cutting through the grains. Okay, so that is what it is. Now, cracks propagates through along the grain boundaries, and then grain boundaries are weakened. So, if you are talking about a material system, maybe there are weak grain boundaries through which external materials can penetrate and weaken the whole material system, or they that is what is embrittled by impurities, or even segregation of material towards the crack location, towards the grain boundaries, etc., which makes them relatively weaker than the grain themselves. Or there may be a case where some of the grain boundaries are weak than the other grain boundaries, which are because of some deterioration mechanisms. Okay. So, corrosion is one such mechanisms which happens when the material is under stress. There is something called stress corrosion cracking. So, this generally happens along the grain boundary. So, different mechanisms of deterioration are there, but for now at this point you need to just understand where the crack happens and what is the reason for that. Okay, so this intergranular crack, here you have the example, the second photograph. You can see here there is a crack which goes like this and then it goes like that. Okay, and here also you can see a crack there, here also you can see a crack there. So, all these cracks are at the grain boundaries, not through the grains. Okay, so it's a difference between trans and intergranular crack. Now, similar, if you want to talk about, this is concrete. Until lastly we were talking about metals, but if you even look in the concrete system, you will see something very similar. When you say you can see aggregates here, this is an aggregate, all these are aggregate, and then you have cement paste that I am going to write it as C, cement paste all around, covering or surrounding the aggregates. Now, you look at this crack here, there is one crack over here which is actually cutting the aggregate. So, I am going to draw the aggregate very closely here. This is the aggregate part here. Okay, you can see it. Let me erase that so that you can see very clearly. So, that is the aggregate which is cracked. So, I can say that that aggregate is actually weaker than the cement paste around it, or the boundary between the aggregate and the cement paste. That is, this boundary is stronger than the aggregate itself. Okay. So, in concrete, typically when we talk about high strength concrete, you will see that most of the times when it breaks, if you take a cylinder and then test it in the laboratory, you will do that in class. So, when you in the laboratory class, when you compress the concrete, it will break, and at that time you will, if you look at the surface of the fractured surface, you will see that in some cases aggregates will itself be broken, and in some other cases you will see that aggregates do not break, but the fracture happens along the boundary of the aggregate, like this here. Okay, you can see this in right here, you can see that. Okay. So, this different types, so that depends on which is weaker material, and then crack will happen through that. Okay.